this is a different structure. It can be drawn in a couple different ways. Okay, I'm going to draw it one way that's legal. I don't want to call it correct. I'm just going to call it legal. This particular structure, C2H4O2. All right. So let me go ahead and draw out the parts of this particular structure, and then we'll start working with them and try to develop a structure that works for this particular molecular formula. Okay. So I've got 2 carbons. All right. So I start off with the puzzle pieces that I have. Okay. I've got 4 hydrogens. I'll use pink for hydrogen this time. There's 1, 2, 3, 4. Okay, 4 hydrogens that are there. And I've got 2 oxygens. All right? 2 oxygens. And what I'm going to use is the same methodology that I used last time. We'll see how well that works for us. Okay? So what I'm going to do is connect 2 carbons together. Right? Just like I did with the previous video. 2 carbons together. And now I'm going to put the oxygens on. Okay? So let's do this. Let's take the oxygens and put 1 at each end. Why not? Okay? Alright? So I put 1 bond in each. Right, now the easy part, I just take all the hydrogens that I've got, and I am going to put them with every single lone oxygen that's there. Okay? So I've got 1, 2, 3, 4, 5, 6 free electrons that need to be paired, and I've got 1, 2, 3, 4. Oh no! What do we do? What are we going to do here? Give it a pause for a second, and I want you to write down on a piece of paper some ideas about what we could do to actually draw a structure here. Good, you got your ideas now? Good. All right, let's see what you got. I can do that by, don't hold it up to the monitor. You're going to look strange in the computer lab doing that. Okay? What am I going to do? There's a couple of options. Okay? I can do something called a ring. And what that means is I can take 2 electrons and stretch them out so that they're connected. So I can do this and take these 2 electrons and connect them so my overall structure looks like this. So I've got carbon, right? There's carbon, carbon, okay? Each one of these has 2 electrons, so still here. But I'm going to move these electrons and put them out on that side, okay? And now what I'm going to do is I'm going to put those 2 oxygens down below. And I've connected those 2 bonds right there. Okay, and I'm going to erase this bond color. I'm going to write it as blue to show you where the bond was formed. Okay, I still have to include the other electrons for those oxygens. These are lone pairs. Generally, they're unreactive. Okay, when doing these types of Lewis structures. So now I've got 4 free electrons, and I can go ahead and I can stick my hydrogens on each one of these. So let's go ahead and do that. All right. Now what I have here is this is a peroxide ring. It's a 4-membered ring. It's got a tremendous amount of ring strain. It's probably going to explode at some point in the near future. Okay? Is this a legal structure? Yes, it is a legal structure. Does the structure exist? No, not necessarily. Okay? These types of structures, so much energy in this particular structure. It's amusing for me, and I'm laughing at myself. But you're looking at it going, this doesn't look wrong. And the reason being is that this is peroxides. Peroxides have a tendency to do very explosive things because they form oxygen gas. And this is a cyclobutane, or it's a 4-membered ring. There's 4-membered rings, not a cyclobutane. Don't say that. Organic chemists can't believe we just said that. Oh my God. So it's a 4-membered ring. The 4-membered rings contain a lot of ring strain. So to break that ring strain, you're releasing a lot of energy. So this thing has 2 very explosive exothermic properties associated with it. All right? So let's not do that. So it's a legal structure. It's just not something that exists. Okay? So let me do something else to show you how this could possibly be. All right? And what I'm going to do is do something with one of these electrons and one of the electrons in the carbon. So in this case, let me use my green here. I'm going to move this electron here, and I'm going to do something called a double bond. So I'll show you what that looks like here. So I've got a carbon, okay, and I've only got one electron here. I've got that one bond to oxygen, okay, and the other bond that got drawn here is this one, okay. I've got a bond to carbon and a bond to oxygen. Okay, how many free electrons do I have at this point? I've got 1, 2, 3, 4. 4 free electrons. Now I'm free to go ahead and slap all the terminus asci. Okay. Put all of those on, and now we have another legal structure. Okay? Is it a legal structure that exists? Probably not. Generally, this would probably polymerize into something that would never be able to resolve in a laboratory. But for the most part, you look at this, and this is a legal structure. Okay? Now let me show you the most common structure that we get with this particular Lewis structure. Okay? In this one, I take the carbon, I stick it to a carbon. Okay? This one has 3 electrons around it. This one has 3 electrons around it. Now I'm going to stick 2 oxygens directly on that carbon. So I'm going to take this one, stick it to an oxygen. All right, and I'm going to take this one up here and stick this one to an oxygen as well. Okay, but I'm going to do that double bond that I did before. I'm going to take that double bond and put that to one of the oxygens. So I'm going to take this one, connect it there, and now what I have is this. Okay. This is that double bond that was down there. All right. This is that oxygen that had the 1 free electron. I've got 4 electrons there. And what I've got here is something that you're actually pretty familiar with. Hydrogen, 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 hydrogen. This particular molecule is called vinegar, acetic acid. If you've ever had oil and vinegar on a salad, congratulations, you have eaten acetic acid and you've lived to tell about it. All right, all it is vinegar. That's all acetic acid is. We can put that together. Notice that I could draw 3 different structures. And there's other structures that I can draw associated with this as well. That would be legal. Would they exist? I'm not sure. Okay? All depends on their energetics and how you make these things. But this one, this is the most common form. It's carboxylic acid. Okay? It's a weak acid. You can stick your hand in it and it's not going to, a bottle of vinegar, stick your hand in it. It's not going to do anything but sting if you've got a hangnail. Okay? At concentrated levels, you can get some corrosion. So if you got glacial acetic acid, don't stick your hand in it. It'll be bad for you. But if you just get that white vinegar from the store, you can pour it on your hand. It's not really going to do anything bad for you. Okay? All right. So that's the basics of Lewis structures. Some other things that you can keep in mind when drawing these Lewis structures. Okay? If you don't have enough hydrogens or halogens to stick around a molecule, remember these things. Remember that you can use double bonds. Those things are perfectly legal. Okay, I can use rings. Okay, rings are perfectly legal as well. And there's one more that's out there, and that's the triple bond. And you guys might be familiar with a molecule, actually quite famous, that involves a triple bond. Okay, N2. If you look at N2, or nitrogen gas, N2, I've got a lone pair and 3 electrons there because it's got 5 valence electrons. And to get these nitrogens to work together, okay, I make bonds between each one of these, and what I get out is a nitrogen, 3 bonds, And you look at it and you're like, well, triple bond, isn't that reactive, Dr. Wayne? I'm like, no, actually it's not in this case. You have triple bonds in the form of nitrogen, okay, make up the inert atmosphere that allows human life to exist on this planet. Okay? If I did something like this, now I've made something called acetylene. If you burn that, you have an acetylene torch. It gets so hot it can melt some certain types of metals. Okay? Welding torches. Acetylene. Okay? So in some cases, these things are highly reactive. Organic chemistry, generally when you get a triple bond, it's going to be very reactive. There's a lot of fun stuff we could do with triple bonds. When you get to nitrogen, it's not so much the case. All right? What about oxygen triple bonds, Dr. Wayne? Well, I'm glad you asked. Okay? Oxygen triple bonds don't exist. Okay, the way I've drawn that works out just fine. Okay? Everything's got 8 electrons. However, if you start with the source here, I've got 6 electrons in each one of the oxygens. So I could draw that. That doesn't mean that it's legal, because I can only form 2 covalent bonds here. So oxygen itself can only be a double bond, and it's going to have 2 lone pairs on the molecular structure. Okay? All right, so that's the basics of Lewis structures. Okay, and I'm going to have you guys, I'll just give you some formulas. And all I want you to do is draw legal structures for Lewis structures. They don't have to be fantastic. They don't have to be all correct. They don't have to exist. All I'm looking for are things that are legal according to the rules. Okay? Good. Glad you liked this one. I can see you smiling through the screen.